Okay, let's get started. So, welcome to your week 9 live session of the GPU architectures and programming course. And let's get started with today's session. So, as always, this will be a 2-hour session. We will have a 5-minute break around 8 o'clock, and we'll mostly be focusing on problem solving. The one difference in today's session will be we'll cover some problems from last week, from week 8, that we had not gone through, because I think some of you had asked me to go through block level and thread level coarsening and then solve those problems, right? So today we have a little bit more content. We will go through all of week 9's problems and the thread and block level coarsening problems from week 8. And additionally, we'll go through the discussion forum questions and the doubts that you guys have asked from the previous session. And post the session, you will have access to the slides and the recording. Okay, I think we'll skip over this. So, week 9 was mostly about OpenCL, right? So, we started off talking about how and why OpenCL originated. We also spoke about how it caters to this heterogeneous set of devices, and then we looked at its language specification, we looked at its platform model, execution model, synchronization, memory model, programming model, and then we looked at some sample programs to kind of understand the program structure also. So this was broadly what we covered, and most of the questions also will focus on the same thing. So let's get started. So first we'll do a quick recap. Again, this is not going to be in a lot of detail. So if you guys have questions and you want me to discuss something in the next live session, since there's no one here today, I'm assuming you guys will watch the recording. If you want me to discuss certain topics, then please leave that as a message in the discussion forum and we can focus on those. So this will be a quick recap of OpenCL. So first, let's start with how this GPU landscape evolved and how OpenCL came into place, right? So first, in the late 90s and early 2000s, that's when GPUs were started to be used as accelerators for various scientific applications, right? And a lot of graphics APIs were in play, like you might have heard of OpenGL, commonly called as OGL, right? OpenCL also you might have heard it called as OCL, right? So all those were there, and then in 2002 there was a new one that came into play called OpenVIDIA. This is lesser known, so you might not have heard of it. Then of course everyone's heard of CUDA, and we have studied it in great detail. So that was around 2006, right? But the thing about CUDA is it was only for NVIDIA GPUs. It was a proprietary language, right? So then shortly after that, Chronos Group, which consists of various industry stakeholders, came together in 2008, which is like a couple of years after CUDA was launched, and defined OpenCL. So again, OpenCL supports AMD, NVIDIA and ARM platforms, and as you will see in later slides, it not only supports GPUs but also various other platforms like DSPs, FPGAs and CPU. Now, coming particularly to OpenCL, stands for Open Computing Language. So as the name says, it's open and it's royalty free, and it is meant for portable parallel programming of heterogeneous platforms, right, across CPUs, GPUs and even other things like DSP. So this includes a language, API, libraries and a runtime system. And it has support for C, C++, Python and Java. Right, moving forward, again we see that it has support for a variety of hardware, CPU, GPU, DSP and FPGA, and this is basically what we mean when we say cross vendor, cross platform. So cross vendor is, if you take GPUs, it not only supports NVIDIA GPUs but also GPUs from other vendors, and then cross platform, you could think of all of these different types of hardware, right? and it's open source, and targets a wide variety of systems, right from supercomputers to your mobile devices. And the good part about this is you write it once and it can be executed anywhere. So it's basically the same code that's going to be executed. And you can kind of balance the load. So if you have a system, let's say, if you have a system, where there is a CPU and there is a GPU, right? Today, a lot of systems are like this, and several of these CPUs are multi-core, right? Let's say you have an 8-core CPU, right? So typically with CUDA, what we do, we end up running the entire program on the GPU. But what you can instead do with OpenCL is to split some part of the work between the CPU and the GPU. So you might have one workload, but you might, depending on the relative capacity, compute capacity of the CPU and the GPU, you might decide that, okay, I'll execute maybe 3/4 of the workload on the GPU, and I'll execute a quarter on the CPU, or vice versa, right? Depending on the CPU and GPU that you have. So OpenCL kind of enables you to do that seamlessly, because you can write the same code and do these things, right? So it allows you to better utilize your system heterogeneity. And today, if you see, right from your laptops to mobile devices, most devices have at least a CPU and a GPU. Additionally, they will also have at least some custom hardware. You might have heard of ASICs, you might have heard of specialized things like TPU, NPU, and a lot of other variations, right? XPU, which are basically custom accelerators, just like the GPU, but they're different, right? So even for those, right? So there's heterogeneity is kind of what's going on in the world right now. So having something like this, OpenCL, and today, if you see, there's a similar proposition that Intel brings forth with its One API, which is also, which I think you broadly look at in the SYCL library, right? So yeah, that's kind of what OpenCL helps you address. Next, coming to some terminology and the correspondence between the CUDA and the OpenCL worlds, right? So this would kind of help you correlate concepts between CUDA and OpenCL and understand what they mean. So what we refer to in CUDA as a GPU is referred to as a device in OpenCL. Again, like we said, OpenCL is not limited to just GPUs. It can be used for CPUs, for FPGAs, DSPs. So the more generic term to use here is device. And similarly, instead of multiprocessor, we use compute element. Instead of scalar core, we use processing element. So basically the idea here is to have terminologies that are kind of hardware agnostic, that do not cater only to a GPU, right? And similarly, instead of thread, you have work item. Instead of thread block, you have work group. Instead of grid, you have ND range. And the different types of memory mapping goes like this. Global is still called global, shared is called local, and local is called private. So this is just some change in terminology that you need to be aware of to answer questions, but the ideas, broad ideas remain the same. So focus on that when you are kind of comparing the two. Okay, moving forward, OpenCL platform model. So a host is connected to one or more OpenCL devices, right? Again, you could have heterogeneous devices. You could have one GPU, one FPGA, and any device is a collection of one or more compute units. So just like your GPU has multiple SMs which have multiple SPs, you can think of it that way, right? And then a compute unit is composed of one or more processing elements. All of these, I think you've seen it in a GPU. Of course, different things have different architecture, so this is just terminology. So I think this should be clear. So broadly, the APIs are divided into platform APIs and runtime APIs. So your platform API is kind of an abstraction layer for diverse computational resources. So you can kind of query. So in class, I think we've seen examples on how to query and get what are the types of computational resources available, and then you can select or initialize compute devices. So you can do all of this using the platform API. And similarly, you can create contexts and work queues. So we'll see a little bit about what these are. Then we have the runtime API, which is used to launch the compute kernel, set the execution configuration for the kernel, manage scheduling, compute, memory resources, and synchronization. So broadly, this is what it is divided into. So if you look at the host program, part of it is the platform layer, which queries the devices, creates the context, and then the runtime creates memory objects associated to context and compiles and creates kernel program objects, issues commands to command queue, synchronizes commands, and then cleans up the OpenCL resources. And then the kernel, as usual, is some C code that you write to perform certain tasks. Okay, let's look at some of these specific terminologies. Context. So the context is created and manipulated by the host using functions from the OpenCL API. So we just saw that uh, there were platform level APIs to create compute contexts, right? So the host uses these APIs to create and change the context. And this is basically a way for host device interaction. It also manages the memory objects that are available to the devices, keeps track of the programs and kernels created for each device. And limiting the context to a given platform helps to utilize a system comprising resources from a mixture of vendors, right? So this is again, when you have heterogeneity in the system, how do you define these things, keeping in mind that you have hardware from multiple vendors? So you will have multiple of these ICDs, right? So that's kind of a design choice that you guys should look at and think about, saying why is this done, what would happen if this is not done, right? Something like that. Next, we look into command queues. So think of this as a queue where you put in. So earlier we just said, when we looked at CUDA, we said we'll write a kernel and then we had host side code to kind of launch that kernel. Here it goes into a little more detail where you put these into a command queue, right? So the host can kind of put them in a certain order into this queue. So this is basically to coordinate the executions of the kernels, and you can queue a set of operations, right? Say kernel 1, kernel 2, etc. And this is some versioning difference before and after OpenCL 2.2. I think you guys can look through that. And yeah, I think this overall gives you an idea. So with this, we come to an end of week 9 recap. Again, I'll repeat, if you have questions on certain topics, because we haven't gone through all the topics that are covered in class, we've only touched upon a select few topics, right? So if you have any other questions or doubts on week 9 content, please drop a message in chat, or even feel free to ask later on the discussion forum. We can go through that in week 10, right? So with this, we are done with the recap. We will move over to the discussion forum. I'll pause here for 30 seconds. If you have any doubts, please ask on chat. Okay, if there are no doubts, let's move ahead to the questions. So the questions for week 9 are mostly very straightforward, right? They are just MCQs based on your understanding of these concepts, not many numericals. So, okay, before that, we have the discussion forum questions. So let's go through that. So I picked out questions that got an answer by yesterday night. I think today in the evening I saw that there were 2 or 3 more questions that were answered. We'll go through that in the next week. Okay, so let's look at this. So this is about what was discussed in class, and here the person says, as per my understanding, we are in a loop for each platform, querying for the type of devices. The fourth parameter, all devices passed here, is all devices num platform 0, and this is making me confused. My understanding is that we must have all devices of I, I0, as we are looking for the GPUs in the ith platform. But the discussion uses num platforms as an index, which actually tries to access entry outside the array size, because the array index ranges from 0 to num platforms -1. So the answer was oh yeah, that is included. So what we'll do is, we'll first solve some example problems, and some of those questions are similar to your question 7 and 8 in the assignment 9. After that, we will also go over the question 7 and 8 in the assignment 9. So I don't want to jump into that. No problem. Yeah. So let's come back to this. Right. So num platforms is actually a number that you've gotten from a previous query, right? So let's say in this case that the num platforms is actually 5. So this array, this index of all devices will range from 0 to 4, right? And since we are in a for loop, we have to actually use the index in the for loop, not this num platforms as the index. So that's what the person who asked this question was confused about, and that's what the instructors or the TAs have also clarified, that it has to be I0 and not num platform 0. And as the person says here, if you use num platforms, you're actually accessing outside the array limit, right? It's an out of bounds error. So yeah, I think this is straightforward. Now this is a more theoretical question. In what way do OpenCL, CUDA, OpenMP, OpenACC, MPI and SYCL differ? And in what ways are they different for doing task parallel or data parallel programming on heterogeneous computing? Is there any literature that discusses the same in detail? So the answer here is just a 2-line definition of each, right? You'll have to look at them a little more in detail if you want to understand them. But this is to give you a high level overview or a starting point. So all of these are parallel computing models, and they also have APIs that are designed to improve the performance of code on multi-core CPUs or specialized hardware accelerators like GPUs, FPGAs, DSPs. But each of them differ in the type of hardware they target. Like we've looked at OpenCL and CUDA so far, right? So at least with these two, you know which hardware they target. You also have looked at the level of abstraction they provide. We've looked at a sample CUDA program and a sample OpenCL program, and you've seen how much more detail or how much more control an OpenCL program gives you. But in contrast, you've seen the programming difficulty also. You see how much extra work you need to do with OpenCL, right? So all of these have similar trade-offs, right? In terms of what hardware they target, the level of abstraction they give you, and also the programming difficulty. That being said, let's look at a couple of lines on each of these. So OpenCL, as we've studied, is a cross-platform API that enables software developers to write programs that can run on CPUs, GPUs, FPGAs and other accelerators. It provides a C-like language for programming and allows developers to create kernels that can be executed in parallel across multiple compute devices. OpenCL also supports task level parallelism and data level parallelism. So I think this part is clear since we've already studied OpenCL. Similarly, CUDA should be straightforward. It's a parallel computing platform and programming model developed by NVIDIA for its GPUs. CUDA provides a C-like language for programming, allows developers to create kernels that can be executed in parallel across multiple threads within a single GPU or across multiple GPUs. Also provides libraries and tools for optimizing performance such as cuBLAS, CUFFT and NVProf. Now coming to OpenMP, this is something we've not looked at, right? So this is an API for shared memory multiprocessing in C, C++ and Fortran, and it allows developers to parallelize loops, functions and sections of code using compiler directives. So there are, for instance, you would have seen hash define, hash include, lots of things like that with C, right? With OpenMP, you can use similar compiler directives to tell the compiler. So let's say you have a for loop, right? Loop 1. You can use a compiler directive before this loop 1, which tells the compiler to parallelize this loop, right? That's how it works. So, and this is supported more widely by modern compilers and can be used to parallelize code on multi-core CPUs and some accelerators. OpenACC is another API for parallel computing developed by Cray, NVIDIA and PGI. Again, enables developers to accelerate their code by using compiler directives to specify parallelism and data movement. Provides a high-level portable abstraction for parallel computing and is supported by most modern compilers. Coming to MPI, stands for Message Passing Interface, and this is a standard for message passing parallel computing. So it allows multiple processes to communicate and synchronize with each other by sending and receiving messages. It's again very commonly used in HPC applications like simulations and data analysis, and can be used to parallelize code on clusters of computers. So both OpenMP and MPI kind of came into play in the HPC era to basically accelerate your scientific applications, but one is a shared memory based paradigm while the other is a message passing based paradigm. You can look up shared memory versus message passing to understand a little bit about the difference between these two. Finally, we have SYCL. So SYCL is pronounced SYCL. It's a single source C++ programming model for heterogeneous computing. So it's kind of a very recent one, and it's similar to OpenCL in that you can write code that runs on CPUs, GPUs and other accelerators. Only difference is here we use C++ syntax and semantics. So again, you get a very high level abstracted programming interface where developers can kind of think of parallelism and data movement as a high level idea without worrying about low level details of the hardware. So overall, each of these has its strengths and weaknesses, and which one you want to use depends on the specific requirements of the application, the hardware and the programming expertise, right? So each of these has certain things that it's good at, certain things that it's capable of, and which one you want to use depends on the particular use case. This is a very high level answer. Again, if you've not worked with some of these, you might be very confused as to what is the difference. So that's why I think you can do one thing. You can go look at a simple sample program, right? Like, I don't know, matrix multiplication or some vector addition. Simplest thing that you can find in all of these. Then you'll see how differently it is written, right? That's one way of comparing it. That will tell you how difficult it is to write. It will also tell you the level of abstraction, how much detail you need to know to program in that language, and then look up what hardware it supports. That will give you kind of a less hazy picture of the differences between these. Right, here's one more question. I think this is the last one. So this one says, if we use OpenCL for FPGA programming, then we don't have to write a separate program in HDL or hardware description language. Will OpenCL take care of both HDL and high level language? So again, we have a one line definition about OpenCL, that's fine. Using OpenCL for FPGA programming does not eliminate the need for writing HDL code entirely. When programming FPGAs using OpenCL, the developer writes code in a high-level language that is then compiled into FPGA-specific HDL code by the OpenCL compiler. The HDL code is then synthesized, placed, and routed onto the FPGA to create a hardware implementation that can be programmed and run on the FPGA. While OpenCL does provide a high-level abstraction for FPGA programming, it does not completely replace the need for HDL code. Instead, it allows developers to express their algorithms and data structures in a high-level language and automatically generates the FPGA-specific HDL code for them. This can make FPGA programming more accessible to software developers who may not have extensive experience with HDLs or FPGA design. So, in one sentence, the answer says that you still have HDL in the picture, but the developer doesn't have to write it. So think about a C program, right? Ultimately, it does get translated to assembly instructions because all your hardware knows is assembly instructions, right? So, but you as a developer don't have to write assembly code, and that makes your life a lot more easier, right? That's what the C language gives you. So similarly, OpenCL gives you an abstraction because of which you don't need to know HDL. You might have been working on the CPU side of things or on the GPU side of things. You might have never used an FPGA, right? So now you don't need to go learn HDL to program for an FPGA. Instead, you can simply write OpenCL code, and OpenCL under the hood will use its compiler to generate HDL code. The HDL code still needs to be in the picture, but the developer need not write it. That's all this says. So with this, we are done with the discussion forum questions. Any doubts on any of these three? All three were kind of theoretical, I think. But if you have any further questions on this, feel free to ask. We'll pause for a few seconds and move to the questions. Okay, I'm guessing there are no questions. So let's move to the questions then. So we'll first start with week 9 questions. They're very straightforward, right? So we'll take a minute or so to answer each question. What is the corresponding term in CUDA for private memory in OpenCL? Okay, how does the tile size relate to local work size and global work size? We'll come to this. I think this is covered in one of the questions that we have for today, and also in the question 7 and 8 of week 9. So we'll come to that. Any answers to this question? What is a corresponding term in CUDA for private memory in OpenCL? You can take a minute to think about it. Local memory. Okay, let's take a look. It is local memory. I think this doesn't need much of an explanation. It's a straightforward question. Let's move to the next one. What is the corresponding term in OpenCL for shared memory in CUDA? Again, we'll take a minute for this. Any answers? Local memory again. That is correct. Again, I think there's no need for an explanation. It's just a terminology mapping. We'll move on. What is the corresponding term in OpenCL for local memory in CUDA? Okay, we have an answer, private memory. Yes, that is also correct. So these are all from the initial terminologies, right? Let's move forward. What is the corresponding term in OpenCL for thread in CUDA? Work item, work group, compute unit, compute core. Okay, work item, that is also correct. Again, I think no explanations needed. Moving forward, what is the corresponding term in OpenCL for scalar core in CUDA? Thread, work item, compute unit, processing element. Okay, we have an answer, processing element, that is also correct. Let's move on. OpenCL context keeps track of the memory and program objects created for a given device. Is this statement true or false? Think about that. Okay, we have an answer saying true, that is also correct. I think we had this definition of context in the recap, right? Where, yeah, here. So manages the memory objects that are available to devices, keeps track of programs and kernels that are created for each device. So where were we? Question 6. Yeah. So that is true. Moving forward. For multiple devices, a single OpenCL context can be created. Is this true or false? Okay, true. This says it is false. Let's go back and see our definition of context. Limiting context to a given platform helps utilize a system comprising resources from a mixture of vendors. Okay, this question, let me actually check. The answer key that was given said false, but I think it is for a single device, not for multiple devices. But I'll anyway check that since you had a confusion. Let me go through the slides once and see if there was some additional information on context. In case there is a change in the answer, I'll make the correction before uploading the slides. But for now, the answer given is false. Let's move ahead. A single command queue can execute only one kernel on a single device. Is this statement true or false? Okay, we have an answer saying true. It's actually false. So this is the part, right? It's not just one kernel. So a command queue is something where you can queue up kernels. So I can do something like kernel 1 followed by kernel 2, etc. It is for a single device, but then I can queue up kernels, right? So that is why it makes it false. It's not for a single kernel. It's for multiple kernels. Hope this is clear. Here, I think the context question, it should have been multiple platforms. Then it would be false. For multiple devices, I think it could still have a single OpenCL context. You could have multiple devices from the same platform because that's what your slides also say, right? It says limiting the context to a given platform, not to a given device. So I think you can take this to be for multiple platforms rather than devices. If it is just devices, then you can assume that it is true. You can have a single context for multiple devices. If it's platforms, then it is false. It can't be cross platform, it has to be for a single platform. Yeah, this one we discussed just now, it is false. Any doubts so far in any of the questions? If not, let's move ahead. Host program can have access to local memory at runtime. Is this true or false? Okay, we have an answer saying false. Yes, that is also correct. I think the memory model shows it very clearly. So you can look at that picture in case you have doubts. But host program cannot access the local memory at runtime. Next one, OpenCL allows synchronization across different work groups. Is this true or false? Okay, we have an answer saying false. Let's look at that. Yes, it is false. It allows synchronization within a work group but not across different work groups. So, this is false. With this, we come to an end of all the theoretical questions. I think we have two more. Uh, yeah, this is the recap of that. So, work group synchronization has constraints on order of execution within a single work group, right? So, you cannot have across work group. Command synchronization is constraints on the order of commands launched for execution. So, what we'll do now, we have two more numericals that are very similar to your questions 7 and 8 in week 9. So, we'll come back. I think we're almost at 8 o'clock. So, we'll take the 5-minute break right now. So, we are almost at 7:59. We'll come back at 8:04 and then solve this. Okay. So, you can take a 5-minute break and come back because this is a 2-hour session. So, we'll resume from there. Okay, let's continue. So, two input matrices for a matrix multiplication kernel, tiled version, implemented in OpenCL have sizes, one second, have sizes 128 into 256 and 256 cross 4096. The tile size used is 32, 32. The hardware can accommodate 1024 threads at max per block. Consider the following OpenCL command for kernel launch. CLNQ ND-range kernel commands macmul to null and global work size ampersand local work size 0 null null. The question is, what is a suitable global work size? 32 128 1, 128 40961, 256 40961, 1024 40961. Any answers to this? I think this is similar to your question 7. But in case you don't know and directly want me to explain, feel free to say that too. We won't spend 5 minutes waiting then. We'll directly look at the solutions. If you want to solve it, you can take 2-3 minutes and solve it. Okay, great. We can jump to the explanation then. Right, so the answer is 128 40961, right? So here, how do you get to this, right? So you have, this is a matrix multiplication kernel. So first of all, remember that global work size is kind of related to your problem size, right? So here we have a matrix multiplication kernel, and let's call this A and let's call this B, right? So you know that if you multiply this, the C matrix that you're going to get is going to end up with 128 comma 4096, right? So this is kind of your output. Now if I wanted one thread to process one element of this, then I would define my global work size. First of all, my global work size would be 2-dimensional because my output matrix is also 2-dimensional. So the final element would be 1, right? These two things, if I make it correspond to these two, then it's essentially like in the CUDA world where you had one thread to calculate one output item, right? It's very similar to that. Here also, our final output matrix is of this size, and if we wanted to have one thread to calculate one element of this matrix, the total dimensions would also be 128 comma 4096, and the third dimension would be a 1. So that's how you get the global work size. Is this clear? So the global work size is kind of related to your problem size. If I changed the problem size, then the global work size would also change. So you've done very similar things in the CUDA domain. We are just trying to translate that now to the OpenCL world. Any doubts here? I'll pause for another 10 seconds before we move to the next question. Okay, this is clear. Great. Now, what will be the suitable local work size? And again, I'm going to assume that you want me to explain right away. If you want time to solve this, let me know. Okay, so let's look at the answer. So here it's 32, 32, 1, right? Why is it 32, 32, 1? So first of all, a simple thing, going back to our data dimensions and your work group here, your local and global work size dimensions, they should match, right? So your third dimension would always be a 1 because you're talking about a 2D matrix. That doesn't help here because all your options have a 1, but still keep that in mind, right? It might not always be the case. Now, how do you decide this local work size? So you're given in your question that the tile size is 32 comma 32, right? So ultimately your local work size should multiply to be that, right? Because again here it's basically like you have a tile of a certain size, and you want a certain number of threads to process these tiles, right? So your number of threads should be equal to the number of elements in the tile. That's one way you can think of it, right? So now you know that your tile dimension is 32 comma 32. So this is all again very similar, right? We looked at this. I think if you don't remember the tiling part very well for matrix multiplication, I'm not explaining that here. You can go look at which week was that, week 5 or week 6, where we had various optimizations of kernels, right? So I think it was week 6. So we had this explanation for matrix multiplication kernel using tiling. So you can go look at that, and that will give you an understanding of tiling. But here we get the local work group size basically from this tile dimensions. So how many of those are there, and how many threads do you need, right? So since you have 32 cross 32, you need 1024, assuming that each thread loads one item, which is a reasonable assumption to make. You need 1024 threads. Now you can either have that as 3232, or you can have that as 1024 comma 1. These two options are first of all ruled out. You can have either of these, but again going with our intuition that the dimensions should be similar to the problem size. So since the problem is 2D, we would like to have the number of threads also as 2D. So we would go with 32 comma 32 comma 1. Right? None of this is kind of explained explicitly in class, which is why I think it's a bit confusing. But think of this as very similar to try to relate this to your CUDA concepts that you've already learned, right? How you define the launch parameters for a kernel, and based on that you can come up with the local and global work size. Now is this clear? Okay, I'm assuming it's clear. Yes. So let's go to one last question. Which of the following are true? OpenCL context keeps track of memory and program objects. For a single device, OpenCL context is not required. Command queue to coordinate execution of the kernels on the devices. Host can have access to local memory at runtime. OpenCL allows synchronization across different work groups. So we've looked at some of these in isolation. Here we are asked about all of these together, so I think it's straightforward. You can take a minute and tell me which ones are true. Option A, 1,3, that is correct. So this one we have already gone through. This also we discussed in the command queue overview. This we already saw, these two we already saw as false. For a single device, OpenCL context is not required. No, it is still required. So 1 and 3 are your true statements. So again, I think that's straightforward. So now coming to the question 7 and question 8, right? I'll directly jump to the answer because we just worked this out. So it should be clear. So it's again a matrix multiplication kernel. Your dimensions are 512 cross 256 and 256 cross 14096. Is the dimension also the same? 512. Okay, no, it is slightly different. So let's go through it. Right. So you have the same global and local work size, and your tile size is 32 cross 32. So now what is the global work size? Remember that the global work size is kind of correlated to your problem size. So if you multiply these two matrices, you get an output matrix of 512 cross 4096, right? And you want one thread to be processing every element of this output matrix, or to generate one element of this output matrix. And since it's a 2D matrix, your third dimension can be 1. The other two dimensions can be these two numbers itself, which is your option D. Okay, suppose our input is array instead of matrix. How to decide global work size, local work size? Again, it would depend on your options, right? Because all of these you can have multiple explanations. Assuming you have a 1D array, you can easily say, for instance, that the other two elements, this is for global work size again, the other two dimensions are 1, 1, and maybe this is length of the array, right? But again, this, all of these things depend on the problem size also, right? It's very similar to the CUDA world, where in the earlier lectures you were given some problems and you were asked what is a good launch parameter for this, right? So think of it in the same way. Given a problem, what would the ideal way to solve this be? How many total threads do you need, and how many threads do you need to solve a subsection, right? So in a simple case with an array, the length of the array would be your first dimension, the other two would be 1 for the global work size. Great, that's clear. Okay, in this question, what is the suitable local workspace? It's the exact same explanation as last time. So you have a tile size of 32 cross 32, so your ideal one is 32 cross 32, since it matches that dimension and the number of threads is equal to the same, right? So I think this is straightforward. So we will skip past this since we are already past 8:15, and I think we have the whole thread level and block level coarsening to discuss. So this concludes week 9 topics. We will now move to the leftover parts of week 8. But if you have any questions on anything from week 9, feel free to ask. I'll just pause for 30 seconds and then we'll proceed with week 8. Okay, I'm assuming there are no doubts. So let's proceed with the recap, right? So broadly we are going to cover two topics in this: thread coarsening and block coarsening. So in parallel execution, as we saw in week 8, there might be redundant memory accesses and calculations. So one optimization that we have is to merge multiple threads into one, and this helps you avoid some redundant work and you get some performance benefits because of that. It's similar to loop unrolling, but only thing is it is applied across threads rather than across loop iterations. This is the broad idea. So again, the beneficial effects, you will need lesser number of threads. Basically, you're coarsening it, right? So it's a very visual thing. So for instance, if you have 4 threads, I now make it thicker in a way, right? That's why it's called coarsening. I now have only 2 threads because I'm going to merge 2 of these into one. So you need to now launch only 2 threads instead of 4, right? So barrier execution is reduced. You need to wait only for 2 of them rather than for 4 of them. And increased number of instructions increases scope for exploiting ILP. That's also one thing. Each thread is going to be doing more work now. So you get beneficial effects because of thread coarsening. You also have some detrimental effects because, again, like we said in the last week, the resource consumption like registers and all that increases for a kernel, and this results in reduced occupancy. So theoretically it might be possible for your SM to host maybe 1024 threads, right? But it also has a register and shared memory limit, right? And because now you're kind of merging multiple threads into one, the register consumption or the memory consumption might increase, and because of that you might not actually be able to use up all of these 1024 threads. So that is your occupancy. Occupancy is the ratio of number of active threads and maximum number of active threads, right? So that's one detrimental effects, and also there is increase in cache pressure sometimes. So you have bad effects too. A simple toy example here. So here we do if GID less than n, GO data of GID equal to GI data. You basically multiply GI data with itself. Now here what we do, we define TID of 0 and 1, and this is 2 star GID plus 0. Basically it's that element itself, and here we add an offset of 1, right? And now we multiply. So each thread now does 2 of these things, right? It multiplies TID 0 with TID 0 and TID 1 with TID 1. This is the with coarsening example. Now coming to coarsening factor, it is the number of times the body of the thread is replicated. So in this previous example it is 2, right? We are repeating this part 2 times. So the coarsening factor is 2, and this gives the best performance depending on the program and the hardware. So remember, with most of these parameters, there is a dimension that comes in from the hardware and there is a dimension that comes in from the program, right? So even in these questions, right, we were discussing global work size and local work size, but always remember that there would be such hardware limits. So sometimes you would end up calculating something that is greater than this, then you cannot accommodate for that because the hardware says this is the maximum that can be done, right? So always whenever you calculate something, make sure and check it with the hardware limits that are given to you and see if that's possible, right? So similarly in thread coarsening, you would get the best performance depending on the hardware, right? And you can decide coarsening factor in 2 ways. One is through static analysis, which, for instance, a very simple version of that is what we are doing through our problems, right? We are trying to calculate theoretically what would be the coarsening factor. But you can also do this through profiling, which is basically set a coarsening factor, run it, try it out, and things like that, right? So with that, we'll go to the types of coarsening. Thread level coarsening, block level coarsening, right? These are broadly the 2 types. So in thread level coarsening, you're doing it within a single block, you're increasing the granularity. In block level coarsening, you're increasing the granularity across blocks. We look at both of these in detail, right? So thread level coarsening, what happens is we apply coarsening at the level of individual threads. So we combine 2 or more threads. Generically, we combine X threads from the same block. Each thread block performs the same amount of work but with fewer threads. This is important. So you have earlier, let's say a very simple example, you had 4 threads, right? Each of them was performing one computation, whatever that computation is. Now I have only 2 threads, but each of those threads is performing 2 computations. This is within a block. So now what happens? The number of threads decreases, but the amount of work I do still remains 4 computations, right here. And again, we know this, each SM has limitations in terms of register, shared memory and runnable thread blocks. These hardware constraints bound how much to coarsen. That's a separate aspect. But remember this, each thread block performs the same amount of work. Now there is this notion of stride length. So in this example, we were drawing 4 threads and we said it's going to become 2 threads, right? Now there are 2 ways that I can combine this. I can combine this thread and this thread, this thread and this thread. This is one way. I'm going to call it W1, right? I can also combine this thread and this thread, this thread and this thread. I'm going to call this W2, right? So here in this case, the stride is 1. The offset between the thread IDs that are to be combined is 1. In this case, the stride is 2, right? So these are 2 valid strides that you can have. So and we have 2 limitations or 2 bounds on this stride length, right? The max and the minimum. So the maximum stride length is the number of threads per block in the dimension where coarsening is applied divided by coarsening factor. So here for instance, I have only one dimension. Let's say this is the X dimension. So the number of threads per block in the X dimension is 4 for me. Now let's say my coarsening factor is 2, right? So my maximum stride length should be less than equal to 2. What happens if I set a stride length of 3? First thread is going to be combined or merged with the 4th thread, but then what happens to these 2, right? So you can think of why this bound is there. Then similarly, we've studied memory coalescing. So the minimum stride length has to be greater than equal to the warp size, so that we have the benefits of memory coalescing. So these are the 2 bounds that we have on stride length. So with this, I think you have a good idea of thread level coarsening. Sorry, I have to rush a little bit because I still have the questions to get to after the recap. So if you have doubts on any of this, stop me and ask, but otherwise I'll kind of continue. Moving over to block level coarsening. Here we combine the work of several blocks into one block. So now the number of threads per block remains unchanged. So the number of executed thread blocks is reduced. So each block has to handle an increased workload. So there each thread had to handle an increased workload. Here the block itself has to handle an increased workload because your number of threads per block doesn't change. We are kind of combining the work of several blocks into one block. So let's say we had 4 blocks now. If I said the coarsening factor is 4 for block level coarsening, now you have one block doing the work of 4 blocks. But let's say we had 4 threads per block in all of these, we are still going to have 4 threads per block, right? Now, resource requirements per block will typically increase, obviously, right? Because you are doing the work of 4 blocks in one block. So you're going to increase your register usage and shared memory usage. This is block level coarsening. Again, you have this notion of stride length, except that now stride length is an offset between the IDs of the blocks that are to be merged. So if I were to show you the same diagram, now the stride length would look like this, right? The 2 ways of having your stride length with a coarsening factor of 2. So again, here the maximum stride length, the formula looks exactly the same. Number of blocks is all the difference in the dimension where the coarsening is applied divided by coarsening factor. Minimum stride length greater than equal to 1, right? That's an obvious one. Here there is no memory coalescing coming into play because the memory access pattern within each block is preserved. Moving forward, so we will solve these two coarsening factor calculations because that's an important one that seems to be asked in many numericals, right? So let's solve the one that's done in class first and then move to the numericals so that you can solve the numericals easily. So here on this GPU we have 15 SMs with a max active threads as 2048, max threads per block as 16, registers per SM 64K, shared memory per SM 48 KB, max shared memory per block 48 KB. Your test data size is 512 MB and data type for the test data set is single precision floating point, which is 4 bytes. Block size for the uncoarsened code 512. Shared memory requirement per block is 512 into this 4 bytes, 2048 bytes. So this is what's given to us. So notice that all of this is hardware specific and all of this is problem specific. So if you change the problem, all of this will change. Now let's go to the coarsening factor calculation. So let's say we want to calculate what is this coarsening factor. So we'll start with thread level coarsening. So now the block size is going to become 512 by x. Basically we saw, right, if we had a block of 4 threads and we set our coarsening factor to be 2, it means that we are going to have 4 by 2. That would be our new number of threads or block size. So similarly, the block size earlier was 512. Yeah, here 512. Now with the coarsening factor of x, the block size will be 512 by x. And then active blocks per SM would be 2048, which is your total number of threads that you can have per SM, which is here your max active threads, right? That divided by block size, right? How many blocks can you have is the total number of threads that are available divided by the block size, which gives you 4x, right? Now for thread level coarsening, the shared memory requirement per block is the same. That doesn't change. Why is that? Think of thread level coarsening, how you combine it. So think about whether the shared memory requirement will increase. It won't, right? So the shared memory requirement per block will remain the same, which is this 512 into 4, 2048. It will remain the same. What will change is the shared memory requirement per SM, because now your active blocks per SM changes, that is 4x, right? So per block you will take 2048 bytes. So if you have 4x blocks, you will take 4x into 2048 bytes. And you are given a hardware limit of max allowed shared memory per SM as 48 KB. This is again a hardware constraint. So now what you do is equate this software limit that you've come up with, 4x into 2048 bytes, with your hardware limit of 48 KB to solve for x. It's a simple linear equation. So 4x into 2048 bytes equal to 48 into, this is kilobytes, so that will translate to 1024 bytes. So now if you simplify this, it comes out to be 6, and going to the nearest power of 2, it comes out to be 4. So this, it gives us the coarsening factor of 4 for thread level coarsening. Is this clear? If this is clear, the rest of the numericals will be a breeze. So take a few seconds to look through this. Let me know if you have doubts. Great. So let's move to the block level coarsening, right? Again, we don't know the coarsening factor, so we are going to assume some x. Now the block size is 512. That's not going to change. Remember that. That's the important thing with block level coarsening. So how many blocks do you have per SM? The same 2048, which is a hardware constraint, divided by the block size, which is 512, because here it hasn't changed. In our previous example, it was 512 divided by x because the block size changed. Here the block size will not change. So it is 2048 divided by 512, which comes out to be 4, right? Now the shared memory per block will change. Remember that. That's important. Here the shared memory per block does not change. It remains at 512 into 4, 2048 bytes. Here it changes. It becomes 2048 into x. And then it's the same. So this is per block. So per SM, what you do, you multiply it with the number of blocks. The number of blocks here is not an unknown, it's just 4. So you multiply it with 4. Then you impose this hardware constraint of 48 KB on your right hand side of the equation. So 4 into 2048 into x equals 48 into 1024. X comes out to be 6. Again, going to the nearest power of 2, it comes out to be 4. Is this clear? This is the second type of question you'll be asked. Block level coarsening. The only difference is these parts, right? Your block size doesn't change. Your shared memory per block changes. Why would it change? Simple, right? You're merging multiple blocks into one block. So the shared memory is going to go up by this factor of x. Very simple. If I merge 4 blocks into one, now this block is going to consume that much more memory. In our earlier case, we merged 4 threads into 2, but in a given block that doesn't change the memory requirements. These 4 threads, whatever memory they consume, now the new 2 coarser threads will also consume the same memory, right? That's the difference here. So other than that, the way you solve this is very simple, very similar, sorry. Any doubts here, or should we move on? Great. So now let's go back to, so we had stopped at this question 6. We had solved question 6, but I'll go through it very quickly so that you can ask me if you have any doubts. So here we have SMs as 20, max active threads per SM is 2048, max thread blocks is 32, register per SM is 64K, and max shared memory per SM is 128 KB. The given kernel performs transpose of a given dataset without any coarsening, right? And your tile dimension is 32, block rows 32. I think we'll skip over this since we had already solved this. The launch parameter for this is as follows: block of 32, 32, 1, grid of 64, 64, 1, and you call the transpose kernel with these launch parameters. Now we are asked to calculate the coarsening factor for thread level coarsening, assuming the coarsened only along x dimension. So let's try and solve that. The answer is 16. So again, the block size, so first of all, the uncoarsened block size is 32 into 32 into 1, which is 1024. Now you're using a coarsening factor of x, so block size becomes 1024 by x. Active blocks per SM becomes 2048, which is your hardware limit of max active threads, divided by the block size, which is 1024 by x. So you get 2x. Now the shared memory requirement per block is the same, which is defined by the block size 32 cross 32 into 4 bytes. Again, I think that 4 bytes was given somewhere. Yeah, here. So it's a float, so it's 4 bytes again. So it's 32 into 32 into 4, which is 4098. This is 4096. This is per block. So per SM, you'll have to multiply it with number of blocks, which is 2x. So 2x into 4096 gives you the shared memory requirement per SM. And your hardware limit is 128 KB. So you equate these two to solve for x. And again, here you get a power of 2 directly. So it is 16, x is 16 in this case. So we had solved this in the previous question, but I think you guys asked for a recap of thread level coarsening. So now is this clear? Any further doubts? I'll pause here for a few more seconds and then we can solve the rest of the questions. Also, I wanted to ask anything from week 10 assignment that you guys have doubts with. We can similarly go through those questions in the next week. If you have questions now, that would be helpful, because if you ask in the next week, then I can only address it in week 11. So if you've already solved it and you have a few doubts or questions, now is a good time to ask. Just put it in the chat window and I'll make sure to solve them next week. Also remember that there are only 3 sessions left. So if you've started revising the course material from week 1, in case you have doubts with any of the earlier content, feel free to ask that also, right? Because after the week 12 live session, there won't be one more for any revision or recap or doubts. So make sure to get all your doubts addressed by the 12th live session. So we have 3 more to go. So if you have any other doubts also, you can ask. Okay, how coarsening factor relates to input data? That's an interesting question. So see, it would ultimately depend on, see here, all these calculations that we have kind of come from our block size and our number of threads per block, right? They come from these launch parameters, and these launch parameters change for a given problem. You know how it changes depending on your input dimensions, whether it's a matrix, whether it's an array. We decide these, right? The block and the grid dimensions. And as these change, the coarsening, the ideal coarsening factor would also change. Here, for instance, if the block size was 512 divided by x, the coarsening factor would also be different from 16, right? So if you were to work that out, let's see, 512 by x, so this is in the denominator, so this becomes 4x, and then this shared memory per block remains the same. Here there's a multiplicative factor of 2, so here also there's a multiplicative factor of 2, so this would become 8. So you can see how the coarsening factor changes with these block size and your number of threads per block, right? And these kind of depend on your problem size. So indirectly your coarsening factor definitely depends on the problem size. It basically, you have a certain level of parallelism that as a developer you express through these launch parameters. After that, we try to kind of merge either threads or merge blocks, and that the ideal factor to do that would be influenced by these parameters and the hardware limits. So it depends on the input data, but it's not a straightforward relation like we saw we saw earlier in the what was that, global work size and local work size, right? It's a little more subtle than that, but it definitely has a relation to both the problem and the hardware limits. Does that answer your question? Okay, great. So now from here we've not solved, so we'll go into the solving mode again. So for the same data as question 6, basically you'll keep this entire part again. So let's quickly scroll through that. 20 SMs, 2048 max active threads, 32 max thread blocks, 64K registers, 128 KB max shared memory, the same transpose kernel with these launch parameters, 32 32 1, 64 64 1. And now we are looking at block level coarsening and calculate the optimal coarsening factor, again coarsened only along the x dimension, 4 8 16 32. So take 2 minutes to solve this, since we looked at a very similar calculation slightly earlier. So try and solve this. Okay, we have an answer. I didn't see that. 16. Let's see. Yes, that is correct. So let's look at how we get to 16. So block size is 1024. Now active blocks per SM, again 2048 from max active threads divided by block size. So you get active blocks as 2. Shared memory requirement per block, 32 cross 32 cross 4 into x. This is the difference with thread and block level, right? Your shared memory requirement basically is proportional to, has a linear increase with x, right? So, and shared, then this is per block. So per SM you just multiply it into number of blocks, which is 2. So you get 2 into 32 into 32 is 1024 into 4, 4096x, and your hardware limit is 128 KB. So 2 into 4096 into x equal to 128 into, this is basically kilobyte to byte, and solving for x we get x equal to 16. So I think this is clear because you've gotten the correct answer. So we have 10 minutes left, so I'll keep moving. Let's go to the next question. Consider the thread level coarsened version of the kernel with a coarsening factor of 4 and the target GPU. For this, compute the total shared memory requirement in bytes per SM. Right? So again, we are sticking with the same hardware factors as in the previous question. So in case you haven't noted that down, ask me and I'll move to that slide. If not, here we are considering thread level coarsening factor of 4. So earlier we were trying to find the optimal coarsening factor. Now we are given a coarsening factor, and instead we are asked for the total shared memory requirement, and note that it is asked in bytes and per SM. So try and calculate this. We'll take 2 minutes. Any answers so far? Is this difficult or confusing? Okay, we have an answer 131072. So let's look at the answer. It is 32768. So let's see how that comes. Shared memory per SM 2 into 4 into 4096. So I think what's been done here is we've just used the formula, right? So remember here we did this calculation 2x into 4096. So we've just substituted for x here. X is 4. So 2 into 4 into 4096, that is 8 into 4096, which comes to 32768. You could also work this out from scratch, right? So let's try out that also. 1024 divided by x, we basically have 1024 divided by 4, which is 256. Now our active blocks for SM would become 2048 divided by 256 or simply 2x, so we would get 8, right? Now the shared memory requirement per block remains this 4096. Shared memory requirement per SM would be 8 into 4096, which comes back to 32768. Hope this is clear. Is there any confusion regarding this? Okay, this is clear. Great. Let's move on. Similar question. Consider thread level quotient version of the kernel. So assume same kernel, same hardware parameters with a quotienting factor of 16 and the target GPU. Now compute total shared memory requirement in bytes per SM. Very similar question. Work it out and let me know when you have an answer. Okay, we have an answer already. 2048. Is that correct? Think about it. Total shared memory requirement per SM. So earlier we had a quotienting factor of 4 and we had 32768. Now we have a quotienting factor of 6. Do you think the shared memory requirement would come down or go up? Simple question. Okay, in the interest of time, let's look at the answer and then you'll kind of understand. So it is C131072, and again 2 ways to calculate this. You can use the formula that you had as 2 into quotienting factor into 4096. Remember that though this 4096 depends on the problem, right? Here it's 32 cross 32 into 4. So this could change. So if you were to write a generalized formula, it would be blocks per SM. It's basically this, right? You need to write what are these terms. So blocks per SM into shared memory requirement per block into quotienting factor. But I would always prefer to work it out from first principles, right? It's just 3 steps, so you can work it out. So again, start with block size, get your active blocks per SM. So here the only difference is the coarsening factor is 16. So everything else remains the same. So our 256 remains 8. Okay, no, all of that changes. Coarsening factor is 16 here, right? So this becomes 64. Active blocks per SM is 2x, that becomes 32, and this 4096 remains. Now it's 2x into 4096. Your x is 16, so it's 32 into 4096. So that comes out, so it's roughly 32 into 4, right? So you can see which one of those matches that. So sorry, this question, this matches that, so it's option C. Now is it clear why it's C and not A? Great. Let's move to our last question for the day. For an effective thread level coarsening across x-axis for a 2D kernel with launch parameters 16, 16, 1, 32, 32, 1, coarsening factor 4, and target platform with warp size 8, the bound for the stride length are. The bounds for the stride length are, you have 4 options. So remember, we discussed how to get this bounds for the stride length for thread level coarsening and block. So this is thread level coarsening. Take a couple of minutes and think about this. Any answers? In the interest of time, I think we'll move to the solution. So, the max stride length is less than equal to number of threads per block in the dimension where coarsening is applied divided by the coarsening factor. There should be an equal to here. So the number of threads, we are saying we are coarsening across the x-axis, right? So the x-axis number of threads per block is 32. So 32 divided by coarsening factor, which is given as 4, gives us 8. So the maximum stride length should be less than equal to 8. Minimum stride length should be greater than equal to warp size to ensure memory coalescing. Warp size is given to be 8. So minimum stride length should be greater than equal to 8. So the bounds for stride length are 8, 8. So your stride length basically can be only 8, because your greater than and less than, greater than equal to and less than equal to come to the same thing. So it has to be equal to 8. That's the answer. And any doubts on this before we wrap up? Great. I think with that we come to the end. I'll wait 10 seconds to see if you have any other doubts, questions from week 9, week 10, anything. If not, we can wrap up. If not, thank you so much for joining, and hope to see you next week, and hope this was a useful session. If you'd like to see anything else covered in the session, please ask. I'll stay on the call for another 10 seconds. If you come up with something, please ask. Otherwise, you can drop off and we can stop here for today. Thank you.